While in the background, we are learning a bunch of surfaces that we could recognize by their equations and their contours. We want to talk about another big tool that we use to deal with calculus, and that would be vectors. These are the same vectors that you encountered in physics. These are the same vectors that you encountered in your engineering statics course. These are the same vectors that you encountered when you took linear algebra. We're just going to do that, put them in a calculus class, and see what we can get out of that. Nothing new about these vectors. It might look a little different, but same vectors. We can see what we care about with vectors right in that first word. A vector is a direction and a magnitude. And we know that direction is a calculus concept. I was checking out your responses to the calculus things discussion. And those are good. And I'm making some comments. Some of you will realize that there aren't any wrong answers. I just want you thinking about calculus things. The calculus concept that we have is direction. Slope of tangent line is an indication of a direction. At every point on that curve, we got a tangent line, and that's indicating that the direction we're headed on that curve at that point. So that's why this vector thing fits into calculus. It's about direction. We need to represent vectors by listing their components. So we're going to represent vectors by listing components. We need one component for each dimension that we're in. Vectors in R2 need two components. We need three components for vectors in R3. Two components for vectors in R2 and three components for vectors in R3. But we're just going to list the components, but we're going to do this in different ways. When we name vectors, we use letters like usual, but we want to differentiate vectors, quantities with magnitude and direction, from scalars, which are just magnitudes. So vectors gets lowercase letter names, but with arrows on the top when we're writing them. We use a lowercase letter and an arrow when we're writing. In print, we might see vectors represented with boldface. Most often when we see vectors in print and they're bold, it's non-italic as well. If you use bold and italic for your vectors, I take off 1,000 points. I'm just kidding. It's no problem as long as we can tell what they are. But when we're writing, since we don't have like bold, I don't know, some of you might be taking notes with a Sharpie as well. That'd be bold. Like not only like in print, that would be bold to do. Through the paper. So when we're writing down vectors, we just put an arrow over the top, and that's how we'll indicate a vector. This is to differentiate from scalars. Scalars are like real numbers, they just have magnitude. We'll use different styles to represent our vectors. Sometimes if we have a vector in R2, we'll just list it as an ordered pair in the same way that we would list a point. To make sure that our reader knows when we're talking about a vector, sometimes we put pointy brackets around a vector. Make sure we're not talking about just points, we're talking about a vector. If we imagine some starting point, the vector 2, 3 will go 2 in the horizontal and 3 in the vertical. And we will indicate, oh, I said -3. We'll go -3 in the vertical and +2 in the horizontal. And we'll have an arrow pointing to horizontal and -3 vertical. And this is our vector V. So we have a horizontal component and a vertical component. We might also list vectors vertically. In which case we'll list our horizontal component first and our vertical component second, reading from top to bottom. We also might list vectors as a linear combination of the standard basis for whatever space we're working in. So we might say this is the vector 2i hat minus 3j hat. So to indicate the vectors I and J, we put little hats on them. I don't know if you can still call it I hat and J hat. I was raised to say I hat and J hat, so I can't stop saying I hat and J hat because they're little hats that you put on I and J instead of just little dots on I and J. Once I saw them as hats, they had to be hats, and it's super cute. Because they're like little gnome hats, little pointy gnome hats. So now I'm imagining gnomes. This one's pretty common. In physics, do you call them I hat and J hat? I'm going to start just saying I and J because it's hard for me to say I hat. Sure, we can name the vectors whatever we want. When we talk about I and J, these are very specific vectors. I is the vector 1, 0, and J is the vector 0, 1. So these are common names for the standard basis in R2. And so 2i minus 3j, we would say, is a linear combination of the standard basis vectors. So the vector 1, 0 is just a horizontal unit vector, I. And the vector j is a vertical unit vector. So we could write this vector 2, negative 3 as a linear combination of the standard basis vectors in R2. For those of you who've been through linear algebra, this linear combination wording is the same linear combination wording that we had before. For those of you who have not been through linear algebra, this is the same linear combination that you're going to eventually see in linear algebra. Linear combination means that we're just going to combine vectors with scalar multiplication and vector addition. So a linear combination means we're only going to combine vectors, I should say, using scalar multiplication and vector addition. This linear combination business is something that we can apply in areas other than just vectors. Another way to think about this is that vectors need not just be horizontal and vertical components. Our vectors could be things like real valued functions. So the vector 2 sine, so for example, the function 2 sine t minus 3 cosine t is a linear combination of the functions sine t and cosine t. And all we did to combine these two is multiply them by scalars and add the functions together. If I had 2 sine t minus 3 cosine squared t, that's not a linear combination of sine and cosine, because I use function multiplication to get cosine squared. So linear combination is a more general term, but we first learn about it when dealing with vectors. How's everybody okay? The scary thing is, I logically know better than to dump more information on you all at once. It's like take a whole big pile of information and just kind of like start pouring it out onto the students. I know better than to do this, and yet still, what happens whenever I walk into the classroom and start pouring all this information out? I gotta really remember, cut it down. Yeah, we're gonna be thinking about these in terms. We're gonna use these to visualize things, and we're gonna want to be so strong in visualizing these things that we don't have to draw the pictures anymore. Because we're about to write vectors in R3. They have 3 components, and all of a sudden, I'm going to lose my ability to draw them properly. So we're just got to imagine little arrows going all over the place. I don't know if memorize is the right word. You just gotta remember stuff. Like all those functions that you remember, like x squared is a parabola, mx plus b is a line. You don't have to memorize those things, but you do have to recognize. You do have to remember. All that trigonometry, like sine of pi over 6 is equal to how much? 1 over 2. Cosine of pi over 6. Root 3 over 2. So these are all things that you just have to know. I don't know if you have to memorize those things, then so be it. If you just remember them, then even better. See, I know better than to just like pour all this information out onto you all at once. And I could recognize when it's happening, unless I'm the one doing it. I know this because I was recently at the hospital and the occupational therapist gave a talk to me and my mom, and it's like so much information. Like, oh, this is too much information. What are you doing? Give us like bullet points, boil this down, give me a TLDR, something. And it's like all this information. And the problem is when you have that much information, it's kind of a liquid form and it's like running through your fingers. And I do that to you in class a lot. And I apologize. I realize it's natural way to explain things. The thing is, I just keep saying the same thing all week. So you just retain some of it one day. Same stuff comes through the sieve. And I remember that one. That's a new one. And then you just kind of like, eventually the sieve gets clogged. I'm just trying to clog your mental sieve. We're going to imagine vectors as just arrows because we need a magnitude and a direction. We have a magnitude and direction. For the TLDR, imagine vectors as little arrows. Too long, didn't read. Imagine vectors as arrows. Longer arrow means more magnitude, and the direction of the arrow indicates the direction of the vector. How's everybody okay? Shorter vector, less magnitude. Immediately wanted to drop some vectors in R3, so we have a harder time just drawing a picture of these arrows and seeing which one is longer. If I just given you vectors in R2, you could just draw them both on the same grid, in the same scale, and just look at them and decide which one is longer. So I'm going to put them in R3, so now it's hard to tell. So in this case, we want to calculate the magnitude of each vector. Yep. So let's find the magnitude or length of each vector. So for this, the tool that we need is the distance formula. We're also going to need some notation because this is math class and we love some notation in math class. For magnitude of a vector, we write the vector's name and then we put not one absolute value, although that would get the point across. We put 2. So that double absolute value symbol, that's our notation for the magnitude of the vector, or the norm of the vector. Then it's just like a distance formula. The square root of the sum of the squares of each component. So the square root of 3 squared. That's just a notation. It's kind of like how much is there, which is absolute value. But absolute value is like, oh, make it positive. We can't just do make it positive. Absolute value of a number is like the length of a number. So it's like, which is why absolute value would work in this scenario. But for vectors, we like to have a different notation because it's math and we love notation. So here are the 9, 10, 16, 26. So we have a square root of 26 and the magnitude of W will be the square root of negative 2 squared plus 3 squared. So we're just extending our distance formula to more dimensions. Because this is the distance formula that we had in R2. In R3, it's just like I'll just put another one on there. In R4, there'll just be 4 terms, still the square root of the sum of the squares. Pythagoras everywhere. So here we get 4, 9, what's that, 13? 13 and 25. What's 13 and 25? So it looks like W is a longer vector. Any questions? The first 2 operations that you need to learn on vectors are scalar multiplication and vector addition. I can do this with 0 minutes left in class because scalar multiplication and vector addition work exactly how you would guess they work. So I'm just going to have you guess how scalar multiplication and vector addition work. These operations work just how you think they work. I could give you a quiz on this right now, except there's no time. I could give you a quiz on vector addition and scalar multiplication and just have you guess how they should work, and that's exactly how they will work. So that's what we'll pick up tomorrow. We'll talk about the 4 different vector operations. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.